Today, we're diving into a fascinating new paper that might just shake up our understanding of the quantum world. Seriously, it suggests that for 100 years, we might have overlooked a fundamental piece of the puzzle, and the answer to a huge mystery could be way simpler than anyone thought. So it all starts with a question that sounds almost childishly simple, but it's one that has kept physicists up at night for decades. Why is electric charge lumpy? Why can't you have half an electron's worth of charge, the same way you can have half a cup of coffee? Why does it always come in these perfect, tiny, indivisible little packets? And this isn't just some weird coincidence, it's a hard and fast rule of the universe. We call it charge quantization. Every single charged particle we've ever found, from here to the edge of the cosmos, has a charge that's a whole number multiple of one single fundamental unit, the charge of one electron. For years, the big question has been, why? Right, so this lands us smack in the middle of a major quantum puzzle. How on earth do you explain this? I mean, some of the greatest minds in physics have thrown some incredibly wild and brilliant theories at this problem.
The usual suspects are, well, pretty mind-bending. One popular idea involves the existence of something called magnetic monopoles, particles we've never actually seen. Another relies on these super complex mathematical ideas called gauge theories. The big takeaway here is that our best explanations have always relied on really exotic stuff, things we can't just go out and find.
But here's the kicker. What if the answer isn't hiding in some undiscovered dimension or some hypothetical particle? What if it's been staring us in the face this whole time, in a concept we all learn about in high school? The researchers behind this new paper asked a really radical question. You know that feeling when a car slams on the gas and you get pushed back in your seat? That's acceleration. What if that very concept, something we experience every single day, was the thing that's been missing from our most fundamental equations about the quantum world? And that's it. The missing piece, they argue, is acceleration. It's everywhere in our world, but it's not explicitly part of the Schrödinger equation, which is basically the main rulebook for quantum mechanics. So they thought, okay, let's see what happens if we put it in. So what do you do if you think the rulebook for quantum physics is missing a key rule? Well, you rewrite it. And that's exactly what these physicists did, starting with one of the most famous equations in all of science. For almost 100 years, the Schrödinger equation has been the absolute foundation of quantum mechanics. It tells us how particles behave, and it works incredibly well. But it has this one little quirk. It doesn't really have a place for acceleration. So, what they did was develop what they call an extended Schrödinger's equation. They figured out a way to mathematically weave in a new term that represents what happens when a quantum particle accelerates. This is the big move, the crucial change to the formula. All right, so now they have this new supercharged equation in their hands, the moment of truth. Could this one simple addition, just accounting for acceleration, finally explain the mystery of quantized charge? And the process they followed was just beautiful in its simplicity. First, they took their new equation and used it to describe a particle getting pushed away by an electric force. Then they did the hard work. They solved the math. And what they found was stunning. The equation only worked. It only gave a sensible real-world answer under one condition. Electric charge had to be quantized. I mean, listen to their own words here. They said the quantization of charge was amazingly observed. It wasn't something they had to force or add in. It just fell out of the math as a natural consequence of including acceleration. The puzzle basically solved itself. Okay, but here's the thing about a really powerful new idea in science. It doesn't just answer an old question. It blows open the doors to brand new questions and entirely new fields of research. And that's exactly what happened here. So naturally, the next question is, what else does this new rulebook change? If it affects how we think about electric forces, what about the other big one? What about gravity? To check this, they did another calculation. They used their new equation to model an electron just sitting in a gravitational field, kind of like the one here on Earth, and looked at its lowest possible energy state. Using the standard, classic version of quantum mechanics, the ground energy for this electron is this unbelievably tiny number, about 10 to the power of minus 33 joules. That's the textbook answer we've had for years. But when they ran the numbers with their new model, the one with acceleration built in, they got a completely different answer, 10 to the minus 27 joules. Now, both numbers look tiny, but that new result is a million times bigger than the old one. This isn't just a tiny adjustment, it's a totally different reality.
The researchers call this a massive enhancement, and it's a huge deal. Why? Because it might just give us a brand new angle on the single biggest problem in modern physics, trying to create a quantum theory of gravity. And this isn't just a bunch of numbers on a page, it makes real testable predictions. These images show a particle's wave function, which is kind of like a map of where it's most likely to be. On the left is the standard prediction, but on the right, in a gravitational field, the new theory says the particles should behave very differently. This is something we can actually look for in experiments.
So let's just quickly recap the whole thing. By taking a fresh look and adding acceleration into the Schrödinger equation, these researchers found a stunningly simple explanation for why electric charge comes in packets. Not only that, but it predicts wildly different behaviors for particles in a gravitational field, maybe even giving us a new path toward a theory of quantum gravity. It's just an amazing reminder that sometimes the biggest answers come from questioning the things we thought we knew best. And that really just leaves us with one final mind-bending thought. If a concept as everyday and familiar as acceleration can potentially crack a mystery that stumped scientists for a century, what other incredible secrets about our universe are just hiding there in plain sight, waiting for us to just look at them in a slightly different way?